Welcome to the second lesson of Module 3, Digital Solutions for Energy Efficiency in Data Centers. In this lesson, we will explore how artificial intelligence can be applied for operating a data center by automating and optimizing the energy use. Data centers are well suited for AI because they are full of sensors and constantly generate a large amount of data. Information like server usage, power consumption, cooling needs, and room conditions create a rich dataset that AI can analyze. AI can study these variables continuously, find hidden patterns, and adjust operations instantly to make the facility more efficient. A key application of AI in data centers is cooling optimization. Traditional cooling systems often operate at fixed set points or with conservative safety margins, leading to overcooling or unnecessary energy use. AI-driven systems, on the other hand, use machine learning models to predict thermal behavior based on server loads, outside weather conditions, and airflow dynamics. They then adjust fan speeds, chiller operations, and temperature set points dynamically. A well-known example is Google DeepMind's application in Google data centers, which reduced cooling energy use by around 40% by letting AI autonomously control cooling equipment. AI is also applied to workload management. Rather than just distributing tasks evenly across servers, AI can intelligently allocate workloads to maximize server utilization, while minimizing idle power. For example, during low demand periods, workloads can be consolidated onto fewer servers, allowing others to be powered down or put into low energy states. During peak periods, tasks can be shifted to servers or even to facilities where renewable energy is abundant at the moment, aligning IT demand with clean energy availability. AI is also very useful for detecting faults and unusual behaviors. Unlike predictive maintenance, which focuses on single pieces of equipment, AI can look at data from the whole data centers, servers, cooling, or network. This helps it spot problems that would be hard to see otherwise. For example, it might notice that certain server workloads combined with airflow patterns always create hotspots, and then automatically move the workloads or adjust fan speeds to fix these issues. Importantly, AI-based optimization requires a robust feedback loop. Monitoring systems collect data, AI algorithms analyze it, and control systems implement changes in real time. This creates a cycle of continuous learning and improvement. The more data the system processes, the more accurate and effective its optimization becomes. Over time, AI can evolve from single parameters tuning to fully autonomous control of subsystems, reducing the need for manual intervention. The benefits of AI-driven optimization are significant. Energy savings can reach 20–30% in cooling and 10–15% in IT utilization, depending on baseline efficiency. But beyond direct savings, AI improves resilience. By balancing loads dynamically and predicting stress points, it reduces the risk of failures and increases uptime. Nevertheless, there are also challenges and risks. AI models require a large amount of high-quality data and must be trained carefully to avoid unstable or unsafe decisions. Transparency is another issue. Operators need to understand why AI makes certain adjustments, especially in mission-critical environments where reliability is paramount. Hybrid approaches where AI provides recommendations and humans validate them before implementation are often adopted during the transition phase. Cybersecurity adds another layer of complexity. As AI systems take on control over critical infrastructure, they also become attractive targets for cyber attacks, making strong protection measures essential. At the same time, reliance on AI raises governance and accountability issues, since automated decisions can still lead to inefficiency, downtime, or even damage if not properly managed. In summary, artificial intelligence has the potential to transform the energy management of data centers. By continuously analyzing vast amounts of operational data and dynamically adjusting workloads, cooling, and power distribution, AI enables efficiency gains that go beyond what humans or static systems can achieve. At the same time, successful deployment requires careful design, robust data infrastructure, and strong oversight. This lesson highlights the role of AI as a dynamic optimizer, complementing the monitoring and predictive maintenance strategies discussed earlier. In the next lesson, we will extend this idea further by looking at digital twins and simulation tools, which allow operators to model data centers virtually and test energy strategies before implementing them in real facilities.